Okay, so this video is going to look at implicit differentiation, and as explained in the content, the difference between an explicitly defined function and an implicitly defined function is whether or not y is isolated. So if we have a function y equals 3x plus 1, the y's by itself are isolated or outside the function. If I have a function like x squared plus y squared equals 16, then y is inside or part of the function, and we say that that is implicitly defined. If I want to find the derivative of something that is implicitly defined, I could solve for y. So I could bring the x squared over and subtract it, and then I'd have a square root to get y by itself. And although we do know how to find the derivative of something that is a square root, it's not as nice as dealing with it before taking the square root. So I'm actually going to start with that one as our first example. So I'm going to look at x squared plus y squared equals 16. And we are going to use implicit differentiation to figure out what is the value for dy dx, the change in y with respect to the change in x. So I'm going to start with x squared. Well, hopefully you know power rule, and the derivative of x squared is 2 times x to the 1 times the derivative of x, which is 1. The reason why I talked about multiplying by the derivative of x, which is 1, is now when I come to this y part, this is going to become 2y. But the derivative of x with respect to itself would be dx, which would be 1, which is why I don't need it. But when I do power rule to y squared, the 2 comes down in front, the y stays the same, the exponent drops to 1, so I no longer need it. But I have to multiply by the inside derivative. And our inside in this case is just y, and the derivative of y is dy dx. So the last step, whenever you differentiate a piece or a part of the function that has a y in it, you have to add in the dy dx. And then I'm going to equal 0 because the derivative of 16 is 0. It's a constant, it doesn't change. Now if I want dy dx, I'm going to solve. I'm going to take this 2x over to the other side, and it's going to become a subtract or a negative 2x. This 2y is multiplying my dy dx, so in order to solve, I'm going to divide, and then if I just clean this up, reduce to lowest terms, I have a 2 on the top, 2 on the bottom, it's going to give me an answer for dy dx of negative x over y. So in the long run, this is a lot quicker and easier than isolating y first and having y equal to the square root of 16 minus x squared, which you would have to think about as 16 minus x squared to the 1/2, then using power rule and inside rule. It's a little bit more difficult. This is not too bad as long as you realize when you differentiate y or anything with a y, dy dx comes into play. The reason we don't have to worry about it when I'm differentiating x is if I'm looking at how x is changing with respect to how x is changing, it's always going to be 1. Let's look at example 2. I have 2xy minus y cubed equals 4. So I'm going to do the derivative of this, but I'm going to have to use product rule because this is two functions times themselves, 2x times y. So the derivative of the first, 2x, is 2 times the second plus the first, which is 2x, times the derivative of the second, and because the second is y, the derivative is dy dx. So that is just the derivative of 2xy using product rule, where 2x I'm thinking of as my first function and y I'm thinking of as my second function. Then I'm going to subtract 3y squared dy dx. That's power rule. The 3 comes down in front, keep y the same, drop the exponent to 2, but because my inside is y, I have to multiply by dy dx, and that equals 0. Because on this side I have 4, which is a constant. Now, first thing I'm going to do is bring everything that doesn't have a dy dx over to this right-hand side. 2y is my only term that doesn't have it, so I'm going to bring it over and it's going to become a subtract or a negative 2y. These two terms here both have a dy dx, so I'm going to common factor out the dy dx. If I take dy dx out of this term, I have 2x, and if I take or factor dy dx out of this term, I have minus 3y squared, so that equals negative 2y. This bracket is multiplying my dy dx, so my last step in order to solve for dy dx is to bring that quantity over to the other side and divide by it. You don't really need those brackets there because this is the only thing on the bottom, but it doesn't hurt to have them there. So dy dx is going to be negative 2y all over 2x minus 3y squared. One more example where we bring this back to the idea of the equation of a tangent. So find the equation of the tangent to x squared plus 4y squared equals 25 at the point negative 3 and 2. So they've given me my x and my y. I need my slope, which is m, so I can go into my modified slope formula that I use to find the equation of the tangent. I can put my x and my y in right away because I know the y value is 2, the x is negative 3, so I end up with y minus 2 over x plus 3 equals m, and then m is the derivative, or dy dx. We work generally with Leibniz notation when we're doing this because if y is inside the function, we don't tend to represent it with f at x, we tend to just work with y. So instead of saying f prime at x, I'm just saying dy dx is the derivative and therefore the slope of the tangent. So there's my function. The derivative of x squared is 2x. The derivative of 4y squared becomes 8y1 times dy dx, and that's going to equal 0 because the derivative to 25 is 0. dy dx is going to equal negative 2x divided by 8y. I brought the 2x over, made it negative. The 8y was multiplying my dy dx, so I brought it to the other side and divided. I'm going to reduce this to lowest terms to get negative x over 4y. And now I know my point is negative 3, 2. So at negative 3, 2, this is going to become negative 3, because it's negative x, over 4 times 2, which is going to give me positive 3 over 8. That is now my m value that I can transfer up to my formula for the slope, cross multiply, so 8y minus 16 equals 3x plus 9, and I'm going to rewrite the line in standard form. My x squareds are already on the right hand side and positive, so I'm going to leave it there, and my final equation is 3x minus 8y plus 25. So that's the equation of the tangent. So there are no new rules associated with this implicit differentiation. The only thing you have to be aware of is when you differentiate y, you have to multiply by dy dx because that's always our inside derivative.